In this session, the basic equation for flow of a fluid from reservoir to well is derived. The equation is obviously derived in radial coordinates, hence it is called the radial diffusivity equation. This is the equation which we are going to derive. 1 by r del by del r k rho by mu r del rho by del r is equal to phi 0 del p by del t. This is p. But this is not the final equation. This equation is non-linear on both sides because both sides are implicitly dependent on pressure. To be precise, the rho that is density implicitly depends on pressure, and there is a density term present on both sides. Hence, the equation is non-linear. So we will also linearize the equation before solving it. Only then the coefficients can be treated as constants, and we can look into the solutions of this equation. Like I said earlier, the basic equation will be derived in a radial form. We will be considering the flow around a wellbore, hence the flow will be from the reservoir into the wellbore. The equation can be solved analytically. We will solve it for various sets of initial and boundary conditions, 3 to be precise. The diffusivity equation can be derived in Cartesian coordinates also, but it is seldom, the equation is seldom used in Cartesian coordinates except in reservoir simulation. But even in simulation for near well flow equation, for near wellbore flow, the equation is used in radial coordinates. Following simplifying assumptions are made. The reservoir is considered homogeneous in all rock properties, most notably porosity and permeability. The reservoir is isotropic with respect to permeability, that is, permeability is same in all directions. Permeability is a tensor quantity, by the way. Lastly, the producing well is completed along the entire formation. So now we consider flow through a radial cell of radius r and thickness dr. The well is assumed to be at the center of the radial cell. The radial cell geometry is explained on the next slide. Okay. So this is the radial cell. This is the well at the center of the radial cell. This is RE. RE is the radius of the radial cell. Okay. And this is RW is the radius of wellbore. Okay, so we will be considering a fluid element. It will be like a hollow cylinder of thickness dr. Okay, and the radius, internal radius of that fluid element is r, and the external radius is r plus dr. Okay, so this is the flow. We have assumed that the fluid is flowing from the reservoir into the wellbore, so the flow will be in this direction. So for this radial cell, okay, we will use mass balance. Okay, so that means mass flow in is equal to mass flow out. Okay, so this is q rho r plus dr, that is the mass flow into the radial cell, and q rho at r. Okay, this is the mass flow out of the radial cell. Okay. So applying the principle of mass conservation, mass flow rate in minus mass flow rate out is equal to rate of change of mass in the volume element. Okay, so q rho that will be mass flow in minus q rho r at r. This one is at r plus dr. This one is at r. Okay, is equal to 2 pi rh. This is the volume of the radial cell into phi. This is the pore volume. Okay. When we multiply 2 pi rh by phi, it will become the pore volume into dr. Okay, this was the circular cross surface area, and 2 pi rh dr is the volume. Okay, is the volume of the radial cell of the volume element. Okay, and multiplied by phi, it becomes the pore volume in the volume element into del rho by del t, that is the rate of change of density with respect to time. Okay, because for now we are not going into compressibility and stuff, we are just assuming that the fluid is compressible. Okay, so 2 pi rh phi dr is the volume of the small element of thickness dr. Okay. The left hand side of the equation can be expanded as q rho r plus del q rho by del r dr minus q rho r. Okay, so the q rho r plus dr, okay, this is expanded as q rho r plus del q rho by del r. It means the rate of change of q rho with respect to r and multiplied by the thickness of the volume element. Okay, that is dr minus q rho r is equal to the r which is remain the same 2 pi r h 5 dr del rho by del t. Okay, which again simplifies to the q rho r gets cancelled. So del q rho by del r is equal to 2 pi r h 5 del rho by del t. Now applying the Darcy law for radial horizontal flow, Q is equal to 2 pi kh r upon mu del p by del r. Okay, so we will substitute this in the previous equation. So del by del r will be 2 pi kh r by mu rho del p by del r. It is equal to 2 pi r h 5 del rho by del p. Okay, so we are taking this. So we can see 2 pi h will be remain constant, so 2 pi h is cancelled out. Okay, it is suggested that you do these calculations for yourself once. Okay, I am just showing how the calculations will be done. So 2 pi and h, these are constants. Okay, so they will be cancelled out. Okay, this r is taken here, is carried here, so it will become 1 by r into del by del r k rho by mu r del p by del r is equal to 5 del rho by del p. Now we will use the definition of compressibility. So from the definition of compressibility, isothermal compressibility, C is equal to minus 1 by V del V by del P, where capital V is the volume and P is the pressure. Okay, so this equation can be modified as C is equal to minus rho by M. Okay, it's 1 by V, so so here small m is the mass. Okay, so volume is replaced by with m by rho. Okay, so minus rho by m del m by rho upon del p is equal to 1 by rho del rho by del p. So this becomes equal to 1 by rho del rho by del p. So c rho del p is equal to del rho. So del rho by del p will be equal to c rho del p by del p. Okay, so substituting equation 5, this is equation 5, in equation 3 gives 1 by r del by del r k rho by mu r del p by del r is equal to 5 0. Now there is no del rho by del p, there is del p by del p. Okay, and this was the equation we intended to derive, and we are now going to linearize this equation. But the thing to see here is that there is the dependent variable here is p, and the independent variables are r and t. Okay, but the reason this equation is non-linear because rho, the density, and in some cases the porosity also is implicitly dependent on P, that is the pressure. Okay, so now we will need to linearize the equation. Okay. So for linearizing, we will have to make some assumptions. Okay, so like I said, equation 1 is a non-linear partial differential equation with the dependent variable as P, pressure, and independent variable as R and T. R means distance from the wellbore, radial distance from the wellbore, and T is the time. Okay, but porosity and density are implicitly dependent on pressure, so that's why the equation is non-linear. Okay. So the equations can be linearized if the compressibility of the fluid is small and constant. Okay, and these conditions exist for undersaturated oil and water. Means undersaturated oil, it's means basically we are assuming that the reservoir is 100% saturated with the liquid. Okay, there is no two phase, there is a single phase liquid. Okay, because gases are highly we cannot consider gases because gases are highly compressible. So that density will give us a lot of trouble in case of gases. In case of liquids like undersaturated oil and water, okay, the fluids can be assumed to be incompressible. So the density will remain constant, almost constant, no matter what. Okay. With these assumptions, now that we know we have assumed compressibility and density to be constant, okay, using the chain rule of differentiation on equation 1, it gives 1 by r del by del r into k by mu rho r del p by del r plus k by mu. This is the chain rule, you can do this calculation, plus k by mu del rho by del r into r del p by del r plus k rho by mu del p by del r plus k rho by mu r into del square p by del r square. This is equal to phi 0 del p by del p. Okay. So now again you can use the definition of compressibility to replace del wherever we have a differential density. Basically we want to replace with differential pressure. Okay. So using this definition, we can again replace wherever there is the occurrence of del rho by del r, we can replace it with del p by del r. Okay. So putting this in equation 16, we get 1 by r del by del r k by mu rho r into del p by del r. This was plus k by mu c into rho into r del p by del r whole square plus k rho by mu del p by del r plus k rho by mu r del square p by del r square is equal to phi 0 del p by del p. For liquid flow, the following assumptions can be made. The viscosity mu is practically independent of pressure, and the pressure gradient del p by del r is small. So del p by del r whole square can be neglected. Okay, this can be done only for liquid flow, not for gas flow. So these assumptions eliminate the first two terms in the LHS in equation 18. So the equation is reduced to del square p by del r square plus 1 by r del p by del r is equal to phi mu c by k del p by del p. Okay, so now we have eliminated all the variables which are implicitly dependent on pressure. Okay, so now there is only one dependent variable, that is pressure, and two independent variables, that are r is the radial and t is the time. These are the two independent variables. Okay. So now this equation has been successfully linearized. Okay, so now we can use this equation to find its solutions. Okay, but this equation given here is valid only for liquid flow. Okay, not for gas flow. So another convenient way of writing the previous equation will be 1 by r del by del r into r del p by del r is equal to phi mu c by k del p by del t. This is simplified by using by compressing the term with the chain rule. Okay. So since compressibility is assumed to be constant for liquid flow, phi mu c by k is also constant. Okay, this is the basic equation has been effectively linearized. However, this linearized can only be applied when C, compressibility into pressure, is much less than mu. Hence the compressibility should be small and constant, which is the case for liquids only. So, liquids and be solids, but not into solids, that is irrelevant. Okay, only thing this linearization is applicable. The compressibility in equation 20 is total or saturation wave. The compressibility of the entire reservoir liquid system is Cp is equal to CO of this is oil, CO compressibility of oil into saturation of oil plus Cw compressibility of water into saturation of water or formate water plus compressibility of the formation. Okay. So basically it's a system. Okay, so we have to consider the compressibility of the system, not just one component. Okay, the saturations are expressed as fractions of pore volume. The product phi and C is conventionally expressed as phi absolute, which means the total porosity, okay, total or effective porosity, into COSO, compressibility of oil into saturation of oil, plus CWSWC plus CF. Okay. Phi C remains same even for pressure presence of cornet water. Okay. Phi C does not change if there is a cornet water, because that only reduces the saturation of oil. Okay, cornet water is immobile, okay, so it will only reduce the pore volume occupied, the hydrocarbon pore volume.